Hello and welcome to Lecture 3 of the Work Unit in Phys 1104. We've learned about the ideas of work, now it's time to calculate work. We'll start with the simple case of work by constant forces. What the idea of work has given us is a new form of conservation of energy. Since the interactions unit, we've had this form, which is valid as long as you're talking about closed systems. But now work allows us to work with non-closed systems as long as they're interacting with the environment via forces. The remaining piece, which we won't do in this course, is to add this one last piece over here by the work, which we call heat. And that turns this into the first law of thermodynamics, which experiment says is about as close to a universal law as you can get. To learn to calculate work, we're going to start with the simplest situation possible. A particle, which has no internal structure, and so there's no possibility of changes to its internal energy, and it's subject to a single constant force. This particle is moving along the x-axis, with a force acting on it parallel to the x-axis. Now this may seem like an extreme idealization only of interest to particle physicists, but actually it's a good approximation quite often for fairly rigid objects. So notice that because it's moving along the x-axis and the force is parallel to the x-axis, this particle must be either speeding up or slowing down, so its kinetic energy is changing. And we can also see that because the force acts right at the particle, the displacement of the particle is the same thing as the force displacement vector. And so the x component of the displacement, which we would just call delta x, is the same as the x component of the force displacement vector, which we'll just call delta x f. And also the force itself is just some x component of the force times I hat, where that x component of the force must either be the magnitude of the force or the negative magnitude of the force. So now we have our definition that the work is the change in energy of the system, and in this case that's equal to the change in the kinetic energy of the system. But be cautious, this is only valid because this is a particle, and so any change in energy is a change in kinetic energy because it has no internal energy. Now we're going to think about some time interval during which the particle goes from some initial velocity to some final velocity, and so it accelerates, and we know from the equation of motion that we can write the x component of the acceleration like so in terms of a sum of x components of forces. But here there is only one force, and so we just have fx over m, or we can rearrange it like this, and that will be a convenient form for us. Now, because the force is constant, this is a constant acceleration situation, and so some old friends from much earlier in the course are going to be useful to us as well. We've now collected together all the equations we need. Let's manipulate them into a useful form. So I can expand the change in kinetic energy out into this form in terms of the final and initial x components of velocities. And now I can use the expression we have for the final x component of velocity and replace it in the equation and get this. Now, notice that I have a Vix that's going to get squared and a minus Vix squared here, and so there's going to be some cancellation. And so expanding out the square and carrying out the cancellation, we have this. Now there's a common factor of ax, which I can factor out, and while I'm at it, I'll factor out a 2 to get rid of the overall 1/2 at the beginning of the equation. So now the equation looks like this. But look at what's inside the square brackets. It's just delta x. And so our whole equation collapses down to this very small form. And I'll remind you that delta x is the same as the x component of the force displacement. Now finally, max is sitting out there in front, and we know that's just the x component of the force, and here we have our useful form. This is the work done by a constant force on a particle in one dimension. Let's look at the sign of this work and make sure it behaves the way we think it should. So in the picture I've drawn, the force and the force displacement vector point in the same direction, and they're both in the positive x direction. And so fx is positive, and delta xf is also positive, and so the work is positive, which means the kinetic energy increases. That's what we expected. We expected that when the force pointed in the same direction as the force displacement, we would get a positive work. Similarly, if it's arranged this way, now that Fx is just negative the magnitude of F. And so that's a negative. And so our work comes out negative. The K decreases as we expect. Well, a single force acting on a particle is an awfully special case, so let's at least generalize to multiple forces. The thing to notice is that our equation of motion, which contained just the one x component of the single force, is just going to get replaced by a sum over the x components of all the forces on the particle. While everything else in the derivation was really just arguments from how 1D kinematics with uniformly accelerated motion worked. And that'll be the same whether we have one force or multiple forces, as long as the forces are constant. And so our final work expression is going to be exactly the same, except with the single force component replaced with a sum of force components. And so this equation is useful enough it deserves a name, and we'll call it the work equation. Let's check your understanding of how to calculate a work by two forces. So here we have a cart that moves 2 meters, and while it moves, there are two constant external forces acting on it, a 5 Newton force to the right and a 2 Newton force to the left. And find the total work done on this cart.